Brilliant. Thank you very much. And now for something completely different. I feel a little bit of a fraud because I'm not an engineer or an engineering geologist, I'm afraid. But I did start my career as a site investigation junior geologist, logging core in a muddy pond and a site called Ferry Road in advance of the Cardiff Bay development area, which kind of dates me, I feel, because it's all now wonderful and swanky and built. So I started my career in this world, and then I discovered remote sensing, and that was me, because I always loved space as well as dinosaurs and other things like that. Anyway, thank you very much for the invitation to come and present this big document that we wrote. Actually, the blurb that I gave you is slightly incorrect, because this guidance document was actually published last year, early last year. But anyway, so it's not exactly new, but we still feel that the need to shout about it a little bit. What I'd like to talk about is why we wrote it, why it was asked for, why it was called for, and the motivation for it and what it's aimed at, etc. What's in it, a little bit about some of the things that we talk about, the methods in practice, and a couple of examples, and a little bit about some of the high-level guidance that we were asked to give, and then some closing thoughts. So the context. Right, so back when we started, which was 2 years prior to the release, we put together a team and a bid for the contract to write this document, and we all recognised that whilst we think that Earth observation is a kind of, or a series of mature technologies, because we're in it, we're very close to it, and we're pushing the edges of it, we sort of take it for granted that everybody else believes and understands that and has already integrated it into what they do. And we discovered and realised through talking to each other that that's not the case. And that there are significant barriers to the uptake of this group of technologies within the engineering, geology and infrastructure and civil engineering community, particularly. And we wanted to do something about it. So we sat down and tried to grapple with what those barriers were. And they included things like fear of cost or not quite knowing how to get started. But the background for all of this, and the importance of it, I should say, is the growth of the space sector in the UK and in the world, across the world. The UK is catching up a little bit, certainly on America and some of Europe. And we have a space agency, and it does things and it funds things. But the growth of the space sector in the UK is is bucking the trend of the wider economy in the UK and has been, as identified by a government report. So the government is actually spending money on this, and it wants to grow the upstream and downstream part of the sector by something like 40% over the next 10 years or something like that. The UK Space Agency has surveyed the tech industries and has found many skills gaps and identified the things that companies are lacking on it. The things that prevent them from getting involved in this technology. So we wanted to write a document that was aimed at companies, people like yourselves, to try and make a bridge between the technology, we're embedded in it, and your needs. That was the idea. And we also recognise there's this growing demand for very precise, objective, wide-scale, accurate, reliable, repeatable, cost-effective information about the ground. And routinely observing satellites are a perfect way to provide that kind of information. And we're sitting right now on the edge of a revolution in terms of data. We're already drowning in the stuff, and over the next 10, 20 years, the number of satellites that will be available, the number of constellations, mean that the spatial detail, the temporal frequency, and the quality of the data that we can get is going to increase hugely. And we're currently now facing the problem of having to develop tools to deal with all of that. So that's kind of the backdrop. My other message is that this is a mature technology. Much of what we're talking about, what I'm going to talk about, and what's in this guide is absolutely mature technology. And then, as an add-on to that, kind of cherry on the cake, last year, the first continent-wide database, live database, growing database of ground motion across an entire continent, the continent of Europe rather, was made public, and this has taken a decade or so to put together, and it's free. It's not at the highest possible spatial resolution that it can be, but as a free data set, it's incredible. The link is over there. Go and if you haven't looked at this, go, as John Davis says, go and waste an hour looking at things that are moving. It's absolutely fascinating. And the idea of it is groundbreaking. The technical challenge is huge to do this. We'd like to do it across the whole of continent of Australia, but we need somebody to fund it yet. Anyway, that's the background. So embedded in what I've just said really here's a list of the things that we wanted to include. We wanted to inform the users and ease their concern about what they might perceive as being a bit expensive or scary or something, or not trustworthy. Maybe there's an idea that the service providers might want to rip you off somehow or not be as good as you think they should be. We wanted to express the state of the art. And so this guidance is on Earth observation, and we spent some time arguing about what that actually meant. And so we've excluded things like airborne data sets and surveys, LiDAR, because it was in the previous Syria guide, and drone imaging, I think. So it's really about satellite imaging. And there's this special focus on radar interferometry, or InSAR as we call it, because that's the way we make very precise measurements about the ground. I emphasize this is not a textbook. It's a guidance document. So we want to give kind of overarching perspective, but allowing people to burrow down to the detail if they want it, and a long way down into the detail. And there are methods and examples and case studies. And the target audience is broad. It's to do anything to do with assets, anybody involved in the life cycle of an asset in management, from the site investigation right through to decommissioning. That's the idea. And we put together a team, an exciting team, which comprised 6 Sense in Barcelona and ourselves in Imperial College in London. And so James Lawrence, myself, Jennifer Schooler, who's now at Sky Geo, Richard Gale, actually, who's in Royal Holloway now. And so that's our author team. And we were supported by a bunch of experts from service providers like Trey Altamira and SatSense, etc., but also Network Rail, Wallingford, Transport for London, and a variety of other people. So we had this huge steering group that supported us and advised us and complained when they didn't like the way we'd written things, and which was actually very time-consuming, but actually very good in the end. And we had the knowledge transfer network to provide a kind of link to industry and help us to get some case studies and things like that. So between us, we realised that we had this huge number of connections through our research collaborations. And of course, 6 Sense's commercial clients. So we felt we were well placed, and we were lucky enough to win the contract. So what is in these guidelines? So as I said, we go from the very basic principles, what is remote sensing, the passive remote sensing using the sun, the solar irradiation, and active sensing from a radar instrument, through to the wavelengths of radiation that we're using and the multispectral bands and how we use them, etc. And some key concepts like defining the spatial resolution of an image data set. And we deal with all of that in some detail in the early part of the data set. And then we moved on to radar and interferometric radar and define that from first principles. And I was thinking that I didn't have an equation in my talk, but actually I do. And it's over there. And it is actually one of my favourite equations. Do I have my, no, I don't. It's over there. It's over there on the right-hand side. It's the magic equation that defines what the phase difference between 2 radar observations is, that gives us the distance between the satellite and the ground to a fraction of the wavelength. 4 pi divided by the wavelength multiplied by the little difference in path length between 2 satellites, because they can never be in the same place twice. So that's my magic equation. And so we explain all those concepts, all the key references, everything's there. Importantly, we talk about things like precision and reliability and accuracy and limitations, situations where things aren't ideal or appropriate or applicable. So we wanted not to oversell what we do within this sphere. We wanted to be realistic and practical. We also wanted, or were asked, to give a kind of overview of the landscape of the Earth observation industry, the upstream part of the technology briefly, and then all the downstream elements, that's the service providers and the link between the satellite and the users. And these two diagrams just give you an idea of the timeline and the number of satellites that have been launched solely with the purpose of observing the Earth, taking images, optical images, radar data, increasing enormously as we come towards the 2020s. And this is going to get bigger and bigger, and the constellations are larger. And that means that the temporal revisit time will get shorter and shorter. And that's good for you guys, people who are monitoring things which change so fast that an observation every 3 days is not enough. So the temporal revisit here is anything between 17 days and daily. So we try to give a kind of a feel for that landscape. And then to the methods themselves, we put together a table for every single broad group of topics, from simple optical image processing, making the image brighter, better contrast, etc., through to change detection and extracting soil moisture and the InSAR methods as well. And so in each case, we gave an overview of what's involved and the kinds of satellite data that you need, some of the advantages and limitations, and importantly, the references that allow you to burrow down if you want to understand more. And so the idea is everything is cross-referenced, so all the different types of remote sensing, the relevant tables, and then also links to the case studies which come next. And then each case study as well is linked back to the methods. So we went through all the major types. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 methods tables. I should be able to remember that, but I can't. And then the most important part really is the illustrations of these techniques in practice, used in anger, in real examples. So we wanted all of the case studies that we included to be industrial, not academic, and not in pure research. And they were designed to show every different kind of method. There are probably more InSAR case studies than anything else, but every method and lots of different asset types and different stages of the construction life cycle, from the site investigation through to ongoing monitoring. And they were kindly provided by these very important organisations here on the left-hand side. And in each case, we give the overall project aims and the methods that were employed, and the kinds of data sets that come out, the life cycle stage, as I said, and at the base of every kind of case study table is a section on the lessons learned. How good was it? How bad? Well, I don't think there are any cases where it was bad, but what was not ideal, or what were the limitations of what was done, as well as the advantages. And there were lots of them. So I'm not going to show any that are actually in the guidelines. I've just got some other examples. So with a large archive of satellites, now in an optical case, we actually have an archive that goes back to 1980 or something like that. It's before that. It's even before that. It's nearly 50 years, I think, for optical data. And for radar, back to about 1992. But if you've got routinely observing satellites, collecting data around the globe every day, the obvious advantage is that you can change detect from one day or 1 week or 1 year to the next. So for things like disaster response, damage to infrastructure, getting aid teams to the people that need them on the ground, high resolution imagery that's delivered within hours of some event occurring is absolutely crucial. So here's an example of the Turkey-Syria earthquake last year, and there's a charity or organisation to deal with geotechnical of problems. It's called Earthquake Engineering Field Investigation Team. And Maxar, which owns the WorldView 3 satellite, which is the highest resolution we have from space currently, which is 31 centimeters per pixel, they gave images of this entire area as fast as they could possibly collect them. And the teams were then poured through the images to find the key areas that were in need of that doesn't work, which were in need of aid. Is the laser pointer? No, wrong one. Here we go. In these circles here, these 5 key areas where there was significant geotechnical damage, and then they deployed their teams, so they saved a lot of time. So the routine collection allows this change detection and also fast response to very, very precisely on the ground is absolutely crucial for responding to disasters like that. Here's another example using radar data to spot automatically fire damage in Khartoum during the conflict there. And so repeating high-resolution radar images are able to detect this strange-looking area up here, which is damaged by fire in a building, an office building, and then again deploy assistance and keep track of these things. So this is done by an algorithm, and it spots change and it flags it up so that then things can be done about it. So disaster response in urban areas is a very important part of Earth observation's role in society. It's not directly related to perhaps what the things we've been talking about today, but that brings me to InSAR, time series InSAR. And this is what it looks like if you're not familiar with it. And here is the portal for SkyGeo in Holland, just to show what the data looks like. It's very pretty. You get a data set of millions of points, measurement points on the ground. Here they're colored by the net relative motion of that position on the ground in terms of its distance from the satellite over a period of time. So it's in reference to the satellite and it's in reference to a starting date. So the red areas are subsiding, any blue areas are heaving, and ideally we'd like to see everything green because that means it's not changing. But what's embedded in this data set, as well as looking wonderfully pretty and impressive, is that each data point has a time series. So this plot here shows that a particular red point, I'm not quite sure where it is, somewhere in here, is subsiding linearly by a substantial amount, 80 millimeters over a period of time. So that means that we can interrogate these data sets and find out what's happening and when it started happening as well, or when it stopped and when it recovered. So it's a forensic tool, basically, to try and describe the behavior of the ground. And I have kindly given an example from Jenny from SkyGeo from Holland. This is a construction site I'm not quite sure where it is. Maybe Rotterdam, I can't remember. And here's the construction site. I've got the wrong thingy. Here we go here. And there's a canal along the side of it, and there's a dam around all parts of the site except on one side where there's no dam wall. And they were dewatering, and what happened very quickly is they started to see cracks in the roads, the pavements, and slight steps in those pavements. Now, these cracks are too small to be seen by the sensor, but we see the effects over a larger area. So the spatial pattern, the spatial context of these measurement points tells us how the ground is behaving. And since this is an insurance case, the big question is, when did this movement begin? So they did some basic InSAR processing and generated a series of points. This is the initial result. So mostly green, but clearly with some red and orange points, so things are moving. Then they refine the processing and filter out any kind of noise. Maybe they start to reduce the coherence a little bit to get more data points where there's vegetated. And then if we start to look at the points that are very near the site, we see this in this circle here. There are a number of points, and we look at the average displacement in that circle, and we see in our time series here scatters of points, And they're kind of subsiding by a very small amount, a fraction of a millimetre over the time period of this study, 2016 to 2021. But there is a population of points that are subsiding very steeply, and these are the red points. And we can see that at a certain point in time, they start to subside by about 80 millimetres a year. So this is obviously a concern. And then if we burrow down a bit more deeply, we can see that most of the subsidences are actually on the paths and the roads. And you look at the time series for this little circle, the subsidence begins on around the 12th of June. And before that, it's pretty stable. Whereas if you look at just the buildings, you filter out everything else and look at the buildings, we see that they are not really having the same pattern as well. There's no big dip in subsidence at that time. So the buildings haven't yet been affected by this dewatering. But what that allowed them to do then was to demonstrate there's a subsidence bowl from the dewatering, and dewatering was stopped on the 27th of August, and we see that have a period of subsidence, and it starts to recover, and the ground eventually heaves back up to normal. So what then allowed them to do is to take some measures and plan their long-term repairs and to make the design rather different. So that's just one example. Now, I couldn't resist showing this, which I hope John likes. And this is not new. I'm sure everybody's seen it. It was in the news, and it's a bit indulgent on my part. I can't resist showing it. One, because it was done by one of my PhD students, and two, because it still amazes me. I keep it on my wall in my office, and people walk past, they'll ask me about it all the time. It's an incredible map of that shows the complexity of ground motion over a short period of time, like 2 years, across a city. And who was it? Somebody yesterday, was it Mark, said, well, it's just the ground, isn't it? It's just the ground. It's just the ground doing what the ground does, right? But it isn't. Look at it. You have areas which are subsiding, the beautiful track of the Elizabeth line and the stations and a variety of other utilities tunnels, which we didn't know about. Blue, the heaving area in the south, and this huge area around Canary Wharf. And then the rest of London is not actually totally green. It's a variety of different colours. And then you can see, if you look carefully, there's some red dots on Blackfriars Bridge, the new Blackfriars Bridge, because that was subsiding quite a lot. And there's a whole bunch of other things in here. And it's amazing that you can, the spatial complexity of the ground behaviour, and when you dig into it, the temporal complexity. Like London comes up and down, hot summers, wet winters, it goes up and down, it breathes as it dries out. So all of these things that we see in this image, many of them have some connection to groundwater, whether it's soil moisture evaporating or dewatering or something. Water is an incredible thing. And if I zoom into the Canary Wharf example, then we see this forensic way we can make time slices through the data set. So here are a series of maps at different time points where we can see 2011 to 2012 subsiding, then heaving, then subsiding, then heaving, and then heaving slightly less so. And if you look at the subsidence track, the time series, you can see where dewatering was stopped, and then it was turning back on again, and we subsided, and then it was stopped, and then it's turned back on again. And those are the points where these images were taken. So the forensic ability of these data sets is both spatial and temporal. I think that's fabulous. And if we zoom in even further onto the Greenwich Peninsula, we discovered that the whole of the O2 was going up and down along with everything else. Everybody was very excited about this. But the canopy is made of fabric, it can't be. No, of course, right? So radar interacts with metal things and hard objects. So it's all the infrastructure inside the O2 canopy that's actually doing the reflecting. But so too is the walkway around the outside of the O2. These wiggly lines here show the track in time of the subsidence of the ground. So it's sort of fairly stable. And then the middle is where most of the subsidence is. So it begins at the top, and through the time series, it subsides down to this sort of level at the bottom, and then it comes back up again. So lots of detail in this data set. And we can also look at complicated things like landslides. And the next talk, I think, is going to do this even more. This is Ventnor, and landslides are challenging. They're lumpy, they move in odd directions, they're wet and they're vegetated, and those things are very difficult for InSAR. But we can still get measurement points, and it's amazing how many measurement points we still manage to get across this landslide. And we can, you can see sort of red points subsiding, blue points are heaving, and you can see how vegetated this area is. But you still get scattering points off hard objects, paths, rocky outcrops, etc. The added benefit of having 2 satellite passes, an ascending one and a descending one, night and day, means that we can decompose the data to extract the vertical and the horizontal components of motion. And again, we start to be able to forensically analyse the way the ground is behaving. Some of this is to do with slip, but some of it may also just be to do with water and causing the ground to bulge and heave. Who knows? And then one last example from GeoFem to do with moisture. They have a model. They use a machine learning-based model which takes the satellite data, optical and radar, and links it with in situ measurements of soil moisture, because radar backscatter changes with increasing soil moisture in a very systematic way, and absorption by the infrared changes in a systematic way with moisture. So we know these things. And here's an example from Singapore. It's a park. And so they've had, from their model, they make a map of soil moisture in this park, and you can see these pale yellowy colours mean almost zero soil moisture. And here's the point in time on the rainfall chart. And then some days later, here, this second point after a storm or some event of rainfall, here now we see that the moisture is increased significantly, and we can draw cross sections and see here's the soil moisture after the rainfall, and here's the soil moisture before. And again, so we have this kind of forensic ability to use these data sets to tell us something about the ground and how it behaves. So anyway, back to the guide. After all the technical detail, one of the things that popped out of this discussions is people need to know how to start. I said, this is great. How do I get in? I talked to my service provider, and then they fire loads of questions at me. I don't know where to begin. I'm confused. So if you've ever stepped through this process yourself, ordering data or planning a project, you realize there's this kind of path you have to go through. And there's a set of questions you will be asked by any service provider, and this is how they budget for what you want. And so getting those questions right and at the right time, at the budgeting part, is absolutely vital. And suddenly changing your mind later on will have a significant impact on your budget. So for instance, right, so you have a long, narrow asset, like a road or a railway or whatever, that straddles urban and rural settings, maybe includes some SSSIs, whatever, and you want a retrospective analysis. You want to see what the ground's been doing over the last however many years. You also want to change, detect, and monitor. So you want kind of benchmark, and you want monitoring in time. It's hundreds of kilometres in length, and you maybe need a measurement every 10 metres or so. And you want to do it over the last 5 years and on into the future. And you want millimetre precision. So, first question, right, so retrospective analysis, that means, okay, it's an individual asset, okay, months and years, yes, and 10 metres or something like that. Ground level measurements at millimetre scale, so that means you need time series InSAR and maybe soil moisture and interferometric coherence. Those are the kinds of data sets you need. If your answers are different, you'll take a different route through this diagram, and you end up with a different, you might need very high resolution data, you might need photogrammetry, you might need LiDAR. So we try to give those scenarios. So in this scenario, you would want a Sentinel-1 radar for retrospective analysis. This is a medium scale mapping tool. It's free data, goes back to 2016. And then you might want high-resolution data for your ongoing monitoring for the next however many years at a 3-day repeat and very, very high resolution. Thanks. So different technologies for different problems. And then we also try to link everything that we had in the guide to the asset cycle, types of assets, and whether we're at the kind of the site investigation stage before, early in the construction, middle, or late stage decommissioning. to try and reassure about the maturity of the technology and the state that it's in, and to provide detail where it's needed, and to improve trust and confidence. I think that's what we wanted to do. So it's a practical guide, and it's the first national guidance or national set of guidelines on anything to do with Earth observation. There are no standards in this industry yet. It seems extraordinary. Maybe this document will be the Kickstarter for some standards. So, particularly InSAR gives you millimetre scale measurements every few days over large areas without the need for any in situ information, precise measurements, retrospectively ongoing. You could think about it as the cost of a couple of boreholes. Can you afford not to use this technology to monitor your asset? That's my take-home message. Thanks very much.